Thank you, everyone. Glad to see everyone here. As you remember, when I gave the original presentation on Valentine's Day 2009, the remote was working. Okay, there we go. I started in the middle of the story. And I told you that when we observe galaxies today, so when we look at galaxies today, we see quite a variety. And we, as astronomers, we like to classify things. And the first thing we do is classify galaxies into three major groups. There's the majestic spiral galaxies. Here are some examples. You see they come in a variety of shapes. Some of them we see edge on, some of them we see face on. They're so pretty that we come up with interesting names for them. There's sombrero galaxy for obvious reasons. So pinwheel galaxy, and the shiner, the black eye galaxy. There it is. Okay. In contrast, the other big group, the elliptical galaxies, you've seen one, you've seen them all. They look like fuzzballs, and they only have numbers. M87, NGC 1132, 13, 16. Sometimes if you're lucky to see some dust in these galaxies. And whatever doesn't fall in those two categories, we call irregular galaxies. But that's a little misleading because irregular galaxies are not just everything else. They have their own properties. They are small, they form stars very vigorously, and some of them, like 1G18 here, are pristine. They seem like they're only beginning their lives now. Their abundance of heavy elements is really small because they're forming their first generations of stars at the moment. The other thing that we observe when we look at galaxies is that they're packed very close together. They associate in groups and clusters. And their separations, as you can see in this picture, their separations are about the same as the size of galaxies, in contrast to stars that are separated by a much larger distance than their size. So as they run around in their groups and clusters, they collide, where they run into each other. Here you see in Stefan's quintet, you see this arc, that's the shock that's formed from the collision of those two galaxies, right there. And the process of collisions of galaxies is an extremely important ingredient, an extremely important process that does a lot to shape the galaxies as we see them today. Here's one celebrated example of merging galaxies, the antennae, and you see many renditions of the antennae here. Let's start with this picture in the middle. That was taken decades ago with the 60-inch telescope at Palomar Observatory. And you see the two galaxies running into each other. You see these long antennae that are pulled out. Those are stars that are being kicked out from the violence of the collisions. As the galaxies come together, and I'll show that to you in a movie in a second, the mutual tidal forces stretch them and throw out stars from each other. Here on the left, you see an image taken in radio waves that shows you where the gas is. Okay, so you see the nice heart shapes. The name of this galaxy is Atoms for Peace. And it was very apt that I showed that picture at Valentine's Day 2003. Okay, the point here is that the gas is directed along the antennae, but some of it is also directed towards the middle. Okay, and if you now look at this part of the image on the right, that's a zoom in of that green box in the middle of the antennae taken with the Hubble Space Telescope so that you can see exquisite detail of what's happening as the gas is funneled towards the center of the interacting pair. It produces a lot of star formation. It's compressed from the tidal forces, and it starts to fragment and form stars. So the stars are responsible, the young stars are responsible for the blue glow that you see here. Those are young star clusters. But in the same process, we also produce a lot of dust from the death of the first generation of stars, and that's the orange glow. The dust is illuminated by the blue stars, and then it re-radiates in the infrared, and that infrared glow is depicted here in orange. So that's the story that we see today. But if we go back and look at the story from the beginning, I can now set the stage for the next speaker. At the very beginning, almost about 200 to 300 million years after the Big Bang, we think that the first stars formed. Okay? Fast forward to about 1 billion years after the Big Bang. At that epoch, we can now see the first fully formed galaxies. And then fast forward 3 billion years after the Big Bang, we know from a variety of observations that most galaxies went through a phase where they vigorously formed stars. They converted all of their gas or a lot of their gas into stars. And that happens to coincide with a period in their evolution where interactions, collisions, and mergers were at their peak. And we think, therefore, that there's a very strong correlation between galaxies colliding, the gas getting compressed, and the stars, most of the stars being formed around that time. Okay? And today, 14 billion years after the Big Bang, the galaxies have the shapes and sizes that we observe. The road to maturity, as I said, involves vigorous collisions. And here's one example. Okay, this is a simulation from my friend Chris Nicholas, who is now at Case Western. The visualization, the nice colors, come from Frank Summers, who's a graphic artist at the Space Telescope Science Institute. And this is an interactive video. It requires audience participation. The challenge for you is to identify where the soundtrack comes from. You get a fully formed elliptical galaxy. Any guesses where the soundtrack is coming from? I'll have one more challenge, another tune from the same soundtrack, and you'll have another chance. Okay, so the big point I made in my previous talk was the missing link. Every galaxy today, every massive galaxy we appreciate today hosts a supermassive black hole at its center. Up until 25 years ago, we thought that the black holes were just passive spectators in the process of galaxy evolution. And starting in the year 2000, our view completely changed. We now have a totally different view. We appreciate that the black holes play a very important and very active role in the formation of galaxies. If they get activated in the process of mergers, that means they have the opportunity to swallow a lot of gas. And by doing so, they convert the potential energy of the infalling gas into radiation. They turn some of the gas around, and that outflow that they create blows out all of the remaining gas from the host galaxies, and it can interrupt the process of star formation very abruptly. In the grand scheme of things, that is a regulation mechanism. It's essentially negative feedback. Those of you who have heard the term negative feedback, you know what it means. The more you force it, the more it resists, and it regulates the formation of stars. Okay, so the next movie shows you this process in action, right? So here you see what the gases do. The stars have been left out of the movie. They were included in the simulation, but they were left out of the movie. You'll see the two galaxies come together. You'll see the shock forming when the gas disks collide. And then what you should look out for is gas being channeled towards the center of each galaxy at first. Then you'll see it starting to bubble up. That's when the black holes get activated. Okay? That's the thermal energy of the gas. Now it's thrown out very big. On the second pass, the two black come together. You don't see them here, but they eventually merge right at the center of the ring. They go through another cloud of fusion, now a more bigger effect, so one cloud and speed up all of the That is a dramatic process and a major ingredient in the evolution of galaxies. This is something that we started to appreciate around 2009. Since then, we have a lot more theoretical work, a lot more. From the soundtrack of Conan the Barbarian. Okay, so to wrap up, since the last time I gave this talk, we've made progress on many fronts. I can't describe everything, but I can tell you that we've done a lot more simulations and we understand the process a lot better. We've detected the molecular gas outflows. Now we can see the gas being blown out of the entire galaxies because of the activity of the black hole. And where we're going next is we're trying to detect the merger. We hope that in about a decade or 15 years from now, we will detect the merger of the two black holes because of the gravitational waves that they emit. In 2017, LIGO detected gravitational waves from smaller black holes. And we're hoping that in the middle of the next decade, the European Space Agency will launch the Laser Interferometer Space Center. 3 spacecraft are arranged in this configuration. When a gravitational wave goes by, it will perturb their positions, make them wiggle a little bit. They'll detect the motion of each other's position, and from there, they'll infer the presence of a gravitational wave. The design has them trailing the Earth. There's the Earth, there's the Leja constellation. Each arm is 2.5 million kilometers in size. They rotate around the sun in 1 year, and the orbits are braided in a sense so that they look towards the interior of the circle and they can cover the whole sky after 1 revolution in 1 year. The launch is going to happen in the mid-2030s. And I can say that with confidence today because the European Space Agency on January 25th announced that it's adopting LISA. That means they're turning on, they're opening their checkbooks and they're starting to spend money in the construction of part. So with that optimistic note, thank you very much. And I'll turn over the microphone to the next speaker.
Okay, is this working? Can you hear me in the back? Excellent. All right, thank you for your patience, everyone. Of course, this is science. It shouldn't work the first time, it never does. So let's go ahead and get started. I'm going to give you an overview of some of the research we've been doing with Webb. Some of this has been in the news already, some has not. It has been a very exciting 18 months. Right? And we'll start here with the launch of Webb. Going to have it launching in the background. This launched from South America on Christmas 2021. Right? And for my field, for people who study the things I do, the most distant stars and galaxies and black holes, the importance of this instrument cannot be overstated. This is something like the Large Hadron Collider or some wonder of the world like the pyramids. And this has been a completely superlative instrument and it has changed my field. It has been a very, very exciting time. And this is the last picture we had of Webb before it flew off into space, and I'll tell you a little bit about what that's like in a bit. But it has been an absolutely stunning 18 months, and I want to tell you all about it. But first, we're going to start a little closer to home. We can't just jump right into Webb. I think it would be a bit overwhelming. We're going to go camping first. A little closer to home. Here, this is Cherry Springs State Park in Pennsylvania, about 2 hours north of here. This is near sunset. You might be here. You can hear the birds chirping, the wind blowing, and the sun's going down. If you stay up a little bit and you look up to the sky, you'll see something incredible. This is the Milky Way. It's actually hovering over us all the time. You just got to look up and see it. Hey, and Cherry Springs happens to be a fantastic place to see it because of the dark skies. Hey, there's a lot to take in here. This is majestic. This is more or less what you would see with the naked eye, maybe a little bit enhanced by Photoshop, but let's not worry about that. But we're going to go somewhere very special. We're not going to go somewhere random in the Milky Way. And we're going to go to the center, right? The galactic core. This is 26,000 light years away. That's an incredible distance. Hey, if you started right now and you were traveling at the speed of light, you went through all of your life, all of your grandparents' life, all of their grandparents' life, all of their grandparents' life, all of their grandparents' life, all the way down, all the way through recorded human history, and you would only be a fraction of the way there, and we would not be there yet. Hey, this is a very, very far way away. We're going to go there. We're going to go there a little faster. Hey, we're going to cheat a little bit. We love Cherry Springs State Park. We're going to go from space. Okay. So we're approximately starting at the position of Earth. This is a real telescope image. Right? And we're going straight to the core. All right, we're going to pass Sagittarius and Scorpius. It turns out they're just illusions of a 2D projection. We're going straight to the center here. One of the crazy things about going to the core, this is an incredibly exotic environment. This is buried under millions of suns worth of dust and gas, kind of like the stuff that comes out of your tailpipe. It absorbs all the light. Something like 1 in 10 billion photons can make it from the galactic core to where we are today. So it is a rare photon that happens to make it to our telescope, a very blessed photon. Right? And because we can't see that well in the visible because of all this dust and gas, we're going to switch to the infrared. This comes from NASA's Spitzer Space Telescope. And the infrared light can peer right through the gas and the dust. And right here, we're looking at the very heart of the Milky Way, at the very core. It's an incredible place, an incredibly exotic place. We have this thing called the nuclear stellar disk. At the very center of the galaxy, it is nothing like our little part of the galaxy, our little local neighborhood. And we have something like 1 billion stars in a tiny volume. If we lived in the nuclear stellar disk, the night sky would be about 500 times as dense. There would be so many more stars. On average, the nearest star is about 1/10 of a light year away. Something like 40 times closer, 30 times closer. And so you would get no rest. The night sky would be very bright here and very striking. But we're not done yet. This is a strange place. It's full of ancient stars, but we're going to go in a little closer to this thing called Sagittarius A star. It's a funny name for something that's truly astonishing. Right, this is the supermassive black hole in the center of our galaxy. It's as heavy as 4 million suns. Right, an incredible number. And we can get a little closer. This is a picture of the very core of the galaxy in the radio. And we're really zooming in here. This picture is about 1,000 light years across, very small to astronomers. And so this is a very exotic place full of high energy events. There's all sorts of things happening here. We have this rings of hot expanding gas, millions of degrees in Kelvin, boiling super hot. We have these supernova remnants from these ancient explosions, a very active place. And then we have this central beating heart, Sagittarius A star, with this funny name. And so we're actually very lucky. 2 years ago, we were able to get a picture even closer to the center here. This is from the Event Horizon Telescope in 2022. This is the first picture of the supermassive black hole at the heart of the Milky Way. Incredibly huge. I promise there's a picture. This is it. This took a long time to take and analyze. It doesn't look like much. It's a little blurry. That's science, right? We're doing it right now. This is the black hole in the very center. Notice it's black, but around it we have this incredibly bright ring. Right? This is a ring of emission. This is very hot gas being sucked into the black hole. It's on its way to the center. To give you a sense of scale, all right, this is about Mercury's orbit, our innermost planet. So this thing is huge. The sun would just be a tiny little dot here at the center. This black hole is very, very large. Right, this is in the center of our Milky Way. This is not weird in a galactic context, actually. There are others. And there's only one that on the scope is about as big as the one in our Milky Way. Right? The one in our Milky Way is very close. There's another one. It is very far away. It is 53 million light years away. Okay, compare that to 26,000 to the heart of the Milky Way. This one's much, much farther away, but it happens to be in a ginormous galaxy. This thing is huge. The stars in this galaxy weigh as much as about 400 billion suns. It's about 10 times the size of the Milky Way. This is a cosmic monster. We're going to go to the core. All right, once again, this core is particularly exotic, but it is even more strange and weird and old than the Milky Way. We're going to go right to the center. This is an artist's impression here. This is not an astronomical picture. But we expect something like a black hole, the mass of 6.5 billion suns. It's something like 1,000 times larger than the one in the Milky Way. It's incredible, all right? What would this look like? Maybe more important, how could something like this possibly form this massive cosmic structure? We have a picture of this one too. This one came out about 7 years ago. This Event Horizon Telescope, combining radio telescopes on opposite sides of the Earth, effectively making the Earth a giant telescope to get this beautiful, beautiful image. This is the black hole, 987. Billions of suns worth of material. It's huge. It is massive. And for perspective, this thing in the middle is something like the black hole. The little wiggle room. Sure. But let me hear. This is Pluto's orbit. Right? So this thing is ginormous. This is where Voyager 1 would be, launched in the 70s, traveling outside the solar system at a very high rate. Still sort of just next to the black hole if we launch from the sun. These things are huge. Finally, we have one that is larger than M87, much farther away. This may or may not be the right mass. It sort of gets a little wiggly here. The way we measure things isn't so good, but in this galaxy, Abel 1201, we have something that is supposed to be 17 billion solar masses. This black hole right here, this is Neptune's orbit. So when we say supermassive black holes, we mean big. These are very, very big. So are these typical? How do we put them in context? Why are they there? These are very natural questions to ask when you see something like this. Okay, how can we explain them? Where did they come from? How did they build? Well, if you ask carefully and you look around the rest of the universe, you can find out that these things are pretty typical. And there's also something very puzzling that suggests something about how they form. So I'm going to show you a plot. I promise there's only going to be a couple. So on the y-axis, how massive is the central black hole? How much does it weigh? And on the x-axis, how quickly are the stars moving around in the core of the galaxy near this black hole? This speed of orbits, I mean, what this really means is how many stars live in the core? How packed is it? So if we look at all sorts of galaxies nearby, we find this relation, this line, where most galaxies live. As the size of the core of the galaxy gets larger, so does the size of the supermassive black hole living in its center. Here's the Milky Way. It's a pretty modest black hole as far as they go. Here, it's M87, which I already showed you. So, what does this mean? This is a clue. This is a very important clue. And it's a clue we don't really understand yet. This was not expected. So as massive as these black holes are, space is bigger, space is much bigger, so their gravity is still too weak to affect the stars. Something else is causing both of these things. As the core of the galaxy gets larger, the supermassive black hole at its center also gets bigger. That's a formation story. We don't quite yet know how to interpret it, but I'm going to take you on a journey. We've learned some things. So, that's what this relationship means. It means they grew up together, they're friends, and they went through high school together. Something like this. There's three scenarios you can kind of draw out here. So what might be happening? We start somewhere in the early universe, the beginning of time. We end up somewhere like today, in a galaxy like the Milky Way. So on the x-axis, this is the formation of the core of the galaxy. How many stars are in the center on the y-axis? How big is our black hole? How much has it grown by eating stuff from interstellar space and intergalactic space? Or emerging other black holes. There's a few lines you can draw on here. This one, it's called symbiosis. They grow together, they're friends. They hold hands, they go through every life stage together. They grow at the same rate. This is something where you'd expect them to be proportional to one another. As the black hole grows, the galaxy grows. And this is one possibility. We also have the so-called dominance theory. And this is where the central black hole grows much quicker than the galaxy. It grows up to be huge very early on. And then the galaxy inevitably follows through some process not yet understood. And so that means, galaxies like the Milky Way, they kind of form around these black holes, and the black hole was there first. Well, right, maybe. Oh. And then we have this other method of growth called adjustments. And this is very different. This is where the galaxy grew first, all the stars were formed, and spectacular bursts of star formation. And then later on, the black hole decides to catch up somehow. This one's hard to explain, I think. So we have a few ideas about how these things might grow and how they might grow up together. But we don't know. We haven't been able to know. Whenever you have a question, as a good scientist, you should start taking data. And here, the best way to figure out why the way things are the way they are. Why is space the way it is? Why are these black holes where they are? Why are they as big as they are? Is to try and understand how they came to be. So what is their formation story? How did they grow up? For that, we have telescopes. This is the Hubble Space Telescope. It is one of the greatest instruments we've ever built. It has been incredible and absolute scientific workhorse. This here is the Hubble Ultra Deep Field. Most of these little dots you're seeing are galaxies, billions and billions of light years away. And so we can use Hubble as sort of a time machine. Explain that in a second. But we can look at things very far away. We'll look at them as they were near the beginning of time. We can figure out what were things like back then. It's like taking an elementary school picture of our black hole and our galaxy. Were they friends back then? Was one of them bigger than the other? We can find out. So what formed first, the black hole or the galaxy core? Hubble can answer that, maybe. And so one of the tricks of the universe is that it's expanding, and it's expanding at an increasing rate. But the expansion of the universe means that light will get stretched. The fabric of space-time is getting larger, and the wavelength of the light in that space-time will also get larger along with it. And additionally, because we are looking at something very far away, billions of light years, in this case, the light takes time to reach it. So light that was emitted billions of years ago is what is reaching us today. So telescopes, the big ones, the ones that look deep into the universe, they function as time machines as well, dramatic time machines. So light from distant objects will come from near the beginning of time, and it will also be substantially red. But we know how to undo these effects. So Hubble's pretty good. Hubble's an incredible piece of technology. It can find these forming galaxy cores at great distances when the universe was only 2 billion years old. Something like 12 billion years ago, most of the age of the universe. We can use Hubble very reliably. What does Hubble see? This happened in about 2009. This happens to be my Ph.D. advisor. Great guy. And this is what they found with Hubble when the universe was 2 billion years old. And what are these? These little dots. What does it mean? Well, some smaller galaxies are still forming their cores full of these ancient stars. But what my advisor found is that most massive galaxies had these cores that were already ancient, and they were even more exotic and dense. So we go back 12 billion years, we're not there yet. We haven't seen the beginning. So these objects are kind of like taking the entire Milky Way and cramming them into a volume 100 times smaller. It's an incredibly exotic place. But Hubble can't see when they formed. We can't see the beginning, and we have to go deeper. What about black holes? Is there anything different happening there? Well, not really. This is the y-axis. I promise I won't show many plots. This is the growth rate of these things, black holes and galaxies. This x-axis is basically time. We call it look-back time. How far back can we look on the universe? And more or less, these black holes and galaxies, as far as we can tell, they seem to grow together at the same average rate. If you average over everything, the black hole grows, the galaxy grows, the black hole grows, the galaxy grows. Right? So if we see these big old ancient cores when the universe was 2 billion years old, we assume it has sort of the same level of black hole. We need to go even deeper. We need to go farther. And so as far as we can tell with Hubble, seems like the most massive black holes and the most massive galaxy cores, the center of these things did form in early times. So what do we need to go farther back in time? Well, Hubble is a fantastic instrument, but it just doesn't observe red enough light to go farther back in time. And it's a technical problem. Hubble can look for all it wants at some point in space, but it's not really going to see very well back in the early parts of time. You can see these bright baby galaxies, but what we want to see are these incredible forming stellar cores. We can't do that with Hubble. And this is where James Webb comes in. And this is why James Webb was built. A very scary experience for those of us. But it went extremely well. Right now, it's up there orbiting in space, doing some incredible science. Explore the early universe together. The Webb telescope is the most expensive telescope ever built by a fair margin. It cost $10 billion. It took something like 25 years to build. It's larger than a tennis court, and it orbits the sun about 1 million miles away from us. We'll talk about the orbit in a bit. But here, this is Hubble's primary mirror compared to a substantial person. Hey, Hubble is about 8 feet across, and this person appears to be maybe 6.5, 7 feet, who knows? They chose a weird one. This is Webb. Hey, 22 feet, a massive thing. It's built itself in space. It's almost 3 times as large as Hubble. So it can see much more detailed objects. Webb has been planned for a very long time. Used to be called the Next Generation Space Telescope. They started planning the launch of Webb 1 year before Hubble even went into space. This was a very long project. They started building Webb in something like 2002. I started my PhD in 2010, and we thought Webb would be launched during my PhD. Luckily, it wasn't, because I didn't graduate in 14 years. Webb wasn't launched until 2022. So this is something like a 35-year process from first idea to planning, to building, to launching, to taking data. It's an enormous investment. Webb is an infrared telescope, and so we have to put it somewhere very special, somewhere very concerning. And so Hubble it's just right outside the Earth's atmosphere. It's basically grazing the atmosphere every time. It's zipping by. We can go up and visit it if we want, say hi, check in, do some repairs. Not true for Webb. Webb, we had to launch into deep, deep space. Webb is living at this special point in space, the Lagrange point, L2, where the gravity of the sun, moon, and Earth cancel out. So it's very happy there. But more importantly, it is very safe here from the glow of the Earth and the sun and the moon. Webb is a very cold instrument. It needs to be cold to see in the infrared, so it needs to be out here in deep space. So this is all good for Webb, as long as it never breaks. And it will never break, right? Right? We're good so far. There's been some concerning incidents, but yeah, if Webb breaks down, we'll never fix it. Okay, it's a piece of space junk at that point. So fingers crossed, right? If Webb works. So it was incredible. It had to build itself in space. It has all of these dangerous things about it, but when it turned on, it started producing incredible data immediately. Right? It had something like 8x the light gathering power of Hubble, and it produces dramatically better images than the previous NASA flagship telescope in the infrared. And this is just comparing it to Spitzer. You just see all of these things pop out of the void. This is the power of Webb. And it can start doing this immediately, right out of the gate. Okay, this thing started showing the stuff we had never seen before, literally right out of the gate. And so we had a lot of big questions we want to answer with Webb. So here's like a cosmic timeline here, starting from the Big Bang all the way to our modern universe here on the left side. And Webb was specifically built to explore the beginning. We only get to explore the early universe once for the first time, and it's happening right now. And Webb is doing it. And so these things, the first stars, the first galaxies, maybe the first black holes, what do they look like? Webb was specifically built to answer these questions. So the first stars are very weird, exotic things. They form out of the primordial soup of the universe, very different than the stars we have today. What do those look like? When did the first galaxies form? People used to put that number at around 500 million years after the universe was born. You will see shortly that is wrong. How did the first black holes form? Did they beat the galaxies? Were they there first? Were they there afterwards? A dominance or adjustment? Symbiosis? And maybe most importantly, what should we be asking? What is it that we haven't even thought of yet? What an incredible thing. If you write down what Hubble was built to discover, the top 10 things Hubble was built to discover, and then you can compare it to the top 10 things that Hubble did discover, there's like one or two items that are on both lists, right? And these telescopes, they're ships of discovery. We're going somewhere completely new. We have some sense of what we're going to find, but most of the things we find, we were not expecting. And that's why these things are so cool. We build them for one thing, and we find all these other things that were on no one's bucket list. What's happening with Webb so far. So like I said, this is the last picture of Webb as it voyaged out to L2. And this is a little retrospective on the Hubble Deep Field. There's an ancient art of pointing telescopes at empty spots on the sky and waiting till you see something interesting. So in 1995, astronomer Bob Williams wanted to point the Hubble Space Telescope at a patch of sky filled with absolutely nothing remarkable. And for 100 hours. It was a terrible idea, his colleagues told him, and a waste of valuable telescope time. People would kill for that amount of time with the sharpest tool in the shed. And besides, no way would the distant galaxies William hoped to see be bright enough for Hubble to uncover. That turned out to not be true. The Hubble Deep Field is perhaps one of the most important astronomical images ever taken. And so with Webb, the first thing we did was take another deep field. Actually, a lot of them. And so when the first data from Webb were unveiled, here, this is President Biden cheering, as the pictures from Webb showed up, the very first ones. And I was watching this telethon as well. I had my colleagues on Zoom. We were all trying to peer over Biden's shoulders, trying to look for little red things. Hey, things from the early universe, trying to discover stuff in the very first images, because that's how powerful Webb is. You can see stuff right out of the gate. It doesn't take much at all. So this is one of the first images released by Webb. This is an incredibly deep image. And it is showing things that Hubble could not see at all. And it shows them, again, right out of the gates. And these data were released mid-July 2022. And they immediately sparked a flurry of discovery, a flurry of papers. And these people who had all these questions that just could not be answered the day before, suddenly the day after, you spend 8 hours analyzing an image like this and you have answers. It's an exciting time, a heady time. And so Webb immediately started breaking records. Immediately. So 5 days after the first Webb data were released, it's July 19, 2022, we identified the most distant galaxy ever seen. And we broke the distance record right out of the gate, 5 days after the first images were released. So here, this is a bunch of different pictures. Here we're a little bit bluer, here we're a little bit better. And you go redder, you see this little dot pop up. This is a direct picture of the earliest stars, when the universe was only 350 million years old. So we already know a galaxy formed at 350 million years, right out of the gate. The first image taken from Webb, galaxies are forming earlier than we thought. And this is the color image. Not so spectacular, but again, this is science. This is what it looks like. This is called Glass Z12. So this record of the most distant object, this was broken again and again and again. Webb has just been an absolute factory for these distant early galaxies, exactly as it was designed to do. One of the most recent ones, 2 months ago, research led by Dr. Bingji Wang here at Penn State, an astronomy and astrophysics department member. She works in my research group. And we found 2 of the most distant galaxies ever seen, another 350 million years after the Big Bang. Here they are, uncover Z12, uncover Z13. And they're actually not little red dots. They have some structure. They look like peanuts or something. They're elongated. And they are remarkably large for the early universe. This was very surprising. We're still not quite sure why. TBD, we need a lot more of these, and Webb is currently going on an Easter egg hunt, trying to find them. Okay. But it's Wikipedia official. We are on Wikipedia. Woo! There's one more distant object than us. They slightly beat us to it. They got lucky. Okay, we'll get them next time. But notice it's very different. It's a very small red dot. Oh, it's ours. Right. So this isn't all Webb has found. Webb has produced this new set of eyes on the universe. And so we're finding things that were just completely invisible before. Here, this is one of the first images released by Webb, and I'm just flashing back and forth between Webb, Hubble, Webb, Hubble. If you see that along you start seeing some things that weren't there before. Some of them are pretty big and bright. Up here, watch this one. Right? This one literally comes out of the void. So we discovered these things in the early Webb data. The lead author dubbed them UFOs. NASA does not approve. This, of course, stands for ultra-red flattened objects. And so these kind of things, you see one right here. This is a zoom in. They were just invisible to the Hubble Space Telescope. And we found whole categories of them. We're still not quite sure what they are, but these are super, super red objects. Hey, they're galaxies in the early universe, when the universe was maybe 2 or 3 billion years old. They're incredibly full of all this dust and gas material, so Hubble just couldn't see them. They were invisible to Hubble. So for Webb, they're bright. They're like lighthouses flaring out in the void, right? They're very easy to spot. So these pop right out of the first data. We think they're some of the progenitors, the ancestors of some of the biggest galaxies today. And this kind of hints at one thing that Webb is very good at. Then we talked at the beginning about how mysterious and strange the core of the Milky Way is. Webb is very good at finding the formation of these cores of these very dense old galaxy centers. And Webb has a particularly well-suited set of instruments for finding the formation of early galaxies, because it's so big and because it observes in the infrared. Another thing we found, this is a so-called Einstein ring. This is an incredible object. This is a very rare thing. This is the most distant one ever seen. And this came out a couple of months ago in Nature Astronomy. What this is actually is 2 galaxies. And there's one in the center. It's very, very small. It's very heavy, and it is way, way in front of the one in the back. And it's acting like a magnifying glass. It's creating a giant ring. So that whole ring here, that's a distant galaxy. That galaxy isn't intrinsically shaped like a ring. It looks like a galaxy, but it's being magnified and spread out. A so-called Einstein ring by the bending of light through gravity. So this is the most distant one ever seen. It happened to be a double lottery ticket for us. Not only is it rare to find one of these things, but it happened to be around a very special type of galaxy. This thing is basically what we think the core of M87, that massive elliptical galaxy we started to talk with. We think this dense little tiny object turns into something like M87. And so this is a very rare thing in the early universe, and we happen to spot it with this very rare geometry that produces this beautiful Einstein ring. That gives us an opportunity to weigh it to extreme precision. And as far as we can tell, this is more massive than we thought by quite a bit, something like a factor of 5. This is very concerning for different reasons. I won't talk about this anymore because I don't know what to say about it. Right? But this is an incredible thing we found. Again, first 18 months of Webb data, right? And it keeps producing. So maybe 10 days after Webb was out, Thursday, a week maybe. My collaborators found something very surprising in some of the first images. But they messaged my grad student, Elijah Matthews, something like 11 p.m. on a Thursday. I was fast asleep, as one should be. Elijah is a night owl. They said, Elijah, are you awake? We need you to fit this new data right now. Elijah was like, oh crap, okay. Let's do it, huh? And they said, I think we broke the universe. And that was the phrase they kept using. I think we broke the universe. And so this analysis went very quickly. And so by 9 a.m. on a Monday, that study was submitted to Nature. Yeah, it's very fast, very fast. But this data were available to the whole world. And everyone was looking at these data, immediately writing up what they found. So it's a very fast-moving field. What did we find? So our team discovered these early universe galaxies, which are impossibly massive, or so it seems. And they were dubbed universe breakers. This is what they look like. Again, these tiny little red dots. They're small because they're so far away. They're red because of the expansion of the universe. And these little red dots were very, very, very bright. We think that they're galaxies, and we interpreted them as galaxies. And if you make a plot, promise there won't be that many of these. That promise gets worse every time I say it. On the y-axis, this is how much these galaxies weigh. This is a logarithmic scale, so every number means it's 10 times more massive. The x-axis is how far away they are in very funny units. So far off to our right is farther away. The very concerning objects are here in red. All the other normal mundane ones we expected are in gray. And just to be clear, this is the mass of the Milky Way. And so some of these are more massive than the Milky Way. They are bigger. And this is when the universe was 500 million years old, 3% of its current age. And this is dumb. This is not what we expected. The Milky Way is a cosmic gas factory. It took billions of years to assemble all of its stars. It had workers going full-time building these stars. And so who are these people to skip the line? Right? This is not how galaxy formation should work. This is kind of like going in to check in on your 2-year-old toddler and finding a fully grown adult in their place. You have questions. All right, and we have questions too. They should not be this large. This was very uncomfortable. And so we're trying to figure out what's going on. We asked the theorists. The theorists are very smart. They know how galaxies grow, and they know that these galaxies grow. It doesn't really matter what the stars are doing. What really matters is the dark matter cocoons that these galaxies grow in. How quickly can the dark matter build? And so they have a pretty good sense of when galaxies should grow, and that's what everyone was thinking would happen. So they went to the theorists and said, hey, these things are way too big. They're way too big. Can you help us explain it? And the theorists replied, well, you're totally wrong, or we broke the universe. If one of these things is true, we're wrong, or we need to change the cosmology of our universe. So this was sort of incredible. Again, right out of the gate, right? And so this hit the news. This was very exciting. I am a mere nerd, a mere office nerd. And I did not expect or prepare for all of this media attention. It was one of the biggest science stories of the year. I had to do a lot of interviews on live TV. This is one of them. I had never done one of these before. They're kind enough to let me tell them what questions to ask me ahead of time. So I wrote down the easy ones. I thought I knocked it out of the park, but the host got about halfway through my list of softballs and then said, hey, let's change the topic. What do you think about aliens? So yeah, I was not ready. I was not worthy, but this was very exciting. This was a huge deal. And so we've gotten more data since then. We've gotten a few more clues as to what these might be. Whatever they are, they're all over the sky. This is another deep field from Webb, totally different part of the sky, totally different team. They find many of these objects. So what are we looking at? Were we right? Are these galaxies? Are they something else? Well, we know one of these three things are true, maybe several, but at least one is true, right? One, our models for understanding galaxies at this time in the universe are very wrong. And I want to emphasize that this is very possible, right? We don't observe how heavy these galaxies are. We assume they're full of stars like the ones in the nearby universe, and then we interpret them in this way. If that's not true, all of that is wrong, and we need to go back to our textbooks. This is very likely true at some level, but these things were extremely massive. We could have gotten it wrong by a factor of 5, and they would still be way too big. So this would not be a small change, this would be a large change, and it would be fascinating in its own right. 2, cosmology in the universe is wrong. The theorists love this. Whenever physicists find something that might be new, they get very excited. They start writing all these models, many different cosmological models that came out that try to explain these things. This is a very high bar. Many pieces of evidence support cosmology, and to break it with something like galaxies, which are so poorly understood, particularly these early times, that's a very high bar. And so I don't think this is right. But there's a third possibility. These are no galaxies. And instead, these are huge feeding black holes. Could be. They're very small, they're very bright. They look kind of like things called quasars. Could be. We just don't know. We need more data from Webb. And so this is still ongoing, but let me briefly explore the black hole hypothesis, some of the other news that has come out from the black hole side. So these supermassive black holes, I already talked about this a little bit. We know that every galaxy has one. They all grew at the beginning of time. We see them light up when they start feeding on gas or stars or flying gas clouds nearby. Okay? And in the nearby universe, these black holes, they're about 1/300 the mass of the galaxy they live in. So 1 to 300 ratio. They're about 300 times smaller than galaxies nearby. How did they get so big? We haven't seen enough growth. We haven't seen them eating enough. They are much larger than they should be based on their diets. So there's 2 basic possibilities here. One, they started out big, and something made them huge at the beginning of time, some sort of primordial process that birthed these black holes, and they came out large, and they only got larger from there. Or 2, they're eating a lot more than we know about. It's got to be one of these things. Which one is it? Webb can answer this. Webb can answer this by finding and trying to weigh the first black holes. So which is it? Did they come out big or did they eat fast? So we found this ordinary little galaxy in one of our deep James Webb images. This was living just about 500 million years after the Big Bang. No big deal. This would have been a record setter 10 years ago. But for us, well, we find these things all the time. It's this little tiny object right here. So what made it extraordinary is not the galaxy and not the stars. But if instead you take an image in the X-rays, because we can't see X-rays, we give them stunning psychedelic colors. And so this thing happens to be very bright in the X-rays, which was very surprising for a few reasons. X-ray photons are rare and precious. This represents something like 20 X-ray photons, incredible treasure trove. And it seems to be coming from this galaxy right here. And so we had to be sure, is this galaxy really as far away as we think it is? We got a spectrum. We pointed Webb again, sat there for something like 30 hours, and got this beautiful data, absolutely stunning, way more beautiful than images to me. And this confirms something, as far as we can tell, some caveats, that this appears to host a supermassive black hole, which is incredibly massive, existing near the dawn of time, and the universe is about 500 million years old, and it weighs the equivalent of 100 million suns. This is huge. This is already 20 times larger than the Milky Way's black hole. Hey, oopsie, that's not right. This is something like between 10 and 100% the mass of the host galaxy. So it's about as big as the rest of the galaxy itself, versus something like 0.3% on average locally. There are some questions about this one. but this seems to very strongly indicate that the dominance theory is correct. And this isn't an well, this is an outstanding piece of evidence. This is a superlative object, I think the most interesting of its class, but many have been found, maybe a little less massive, maybe a little closer, but still of the same category. And this isn't a one-off thing. The universe appears to be full of them, these huge black holes that formed at the beginning of time. And so this is awesome. Artist's image, right? But this poses another question. What incredible physics could produce such an incredibly massive black hole so early? 100 million suns. That's huge. The universe was only 500 million years old. We just don't know yet how they got so big so early. There's a few ideas, something exotic, like a so-called direct collapse black hole. So instead of going through the normal production pathway we have for producing black holes, we could have a huge amount of gas just directly collapse into a black hole immediately, form a giant thing at the beginning of time. Or some other way to create so-called primordial black holes. Before we created all these stars, these black holes had to grow somehow. And I'm not going to get into this too much. But there's more data coming. So these very little red dots, the very bright ones, the ones at the beginning of time, there are two competing teams that independently propose more Webb observations that will pin down exactly what these are. And we found this one thing, it's a very massive black hole. We found a bunch of other black holes. We still have these incredibly bright, they're called little red dots now. That's the name of their stuff, little red dots. So what are these? Are they the cores of massive galaxies? Are they huge supermassive black holes? Or, my bet, if I have to guess, I think they're both. We have some incredibly violent sphere of star formation and feeding black holes in the early universe. And we're seeing both at the same time. If I had to place any money on it, that hole. But we have these two competing teams. We're getting data very soon, March 2024, next month. And we'll find out exactly what these are, and I am stoked. For one, I'm not a betting man. I'm a betting team. I don't like to play the odds. This one is happening about 9 days before this one, but this one's going a little deeper. So whichever one's better, that's what we'll stick with. Okay. But yeah, well, no, March 2024. Okay, so more to come, and I think I'm incredibly excited to see what is out there. And so this is Webb. There's already spectacular discoveries in the early universe. And it seems we might have answered some of the questions we posed at the start. Massive galaxies are definitely forming far sooner than we thought. Whether or not these universe breakers are breaking the universe, there are other observations suggesting galaxies are churning out stars way faster and earlier than we expected. Many different independent observations of these black holes, which appear to be way more massive than we'd expect based on their stars, supporting the dominance theory. Still early times. But all of this seems to be coming out of Webb, and Webb is really just getting started. And most of Webb data, if it lives out to its 20-year timeline, maybe beyond, is still yet to be taken, and many of it hasn't been released by scientists yet. So there's more to explore. And let me end on one last note here. Let's assume there was some cosmic vending machine. It transforms money into knowledge. You swipe your credit card, out comes facts. Pretty cool. How much money would you pay for this vending machine? In order to no other life exists on other planets. One of Webb's core goals. Another exciting thing happening. See the birth of the first stars. Webb hasn't seen a so-called population 3 and original star yet, but I think it will. Or map the universe out to the great impenetrable cosmic fog. We discover all these incredible things about the origin of our galaxy and the craziest things in it. And so how much money would you pay this cosmic vending machine? Stop, think about a number. Lunch is like, what, $20, right? You pay a lunch, right? Maybe a couple lunches. Full tank of gas, $100 to see life on other planets, to see the birth of the very first stars. Hey, Webb costs about $30 per person. That's how much it costs you to know all these things. So it's, one of my friends says, James Webb is witnessing the birth of stars until the edge of times for what US consumers spend annually on potato chips. So I hope it's worth it. Thank you all.